review of last week. The big thing to pick up from last week was whenever you have two lines that are intersected by a transversal, you can use alternate interior angles or corresponding angles, and the fact that a line has 180 degrees to solve for a lot of angles. Those two components are used in the gathering of data to solve problems. I think that was really the big takeaway from last week. That was principles 1 through 6 is what we covered. Starting on page 7, we have a couple more definitions. By the way, before I jump into this, we're going to run through the last principles 6 through 10, or actually there is no 6, 7 through 10. We'll go through those, and then I've got a quick deal I want to review as far as principle 8, which many of you have seen before. It's a review, but we're going to look at some story problems and how we can use those to solve. I want to make sure you can run your calculators correctly also. So we'll do some work on the board with that. If time permits at the end, we will then go into unit conversion. That will be your first assignment that you take home with you. If we're pretty close, I'm going to chop it off if I don't have enough time to get through it, and we'll pick it up next week. All right, so starting on page 7. We have a few definitions right off the bat. Right here they have congruent triangles. Congruent is a word that basically means the same. And if you read through here, you're going to find that if two triangles are the same size as each other, everything's equal with them. Congruent, they're equal. Makes a lot of sense, right? I take one shape that's the exact same as another shape, paste it on there, everything's going to be equal, angles, sides, right? Now, the reason that's fairly self-explanatory when you have two triangles that sit right next to each other. Really, the important part to remember on this is a lot of times on a drawing or in real life, we'll get triangles that are separated by a substantial amount of distance or even on different planes, and they're the same, and people don't make the connection between them and say, oh, this one looks this way, even though it's over here. I got the same one over here. They're the same. I can use that information to solve problems off of one or the other. So basically, congruent triangles are the same. The important one that really helps you for solving problems is down below it, similar triangles. Because this one, you end up using quite often in calculations. Now, based on where this is going, I'm going to come back to it in a minute, but if all the angles on a triangle are the same, the triangles are similar. Now, when a triangle is similar, what we mean by that is it's proportional. Okay? So if I took one triangle like this one, and I scaled it up to this size, and I scaled it globally, all the same, then they're going to be similar because the angles don't change. Now the length of the sides change because I scaled it, right? But the angles don't. This is where it gets valuable. Now, we can, since the sides are proportional, what it's basically saying, here's the short side of this triangle, here's the short side of this one. If I know those two, I can generally solve most of the sides on both triangles by setting them proportional to each other. And I'm basically doing a proportion calculation. I do need to know one other thing, and we'll come back to that in a minute. But how do you know they're similar? All the angles are equal? They're similar. Right? So that's the first thing. If you turn the page, they give you a couple other clues. Down on principle 7. If two triangles' sides are parallel, they must be similar. Okay. If two triangles' sides are perpendicular, they must also be similar. I'm on page 8. Okay. Additionally, if I take any existing triangle and I change one line to another location, so I just take that side and I draw a line parallel to it. The two resulting triangles, this one and the original one, must be similar. Okay. They have to be, because the angles don't change. So you look for all of those conditions. Are the sides parallel? Are they perpendicular? Are the angles the same? If they are, they're similar. Therefore, you can use proportions to solve for missing sides. Now, they also give you one more down here that you can also use. That is if you have any right triangle and you bisect that triangle by drawing from the 90-degree corner perpendicular to the hypotenuse, the two triangles created, this one and this one, have to be similar. They're also similar to the original.
Oh.
Okay? So that's a nice thing too, because we get a lot of right triangles, we want to break them up. That's a good way to break them up, and then figure out these different sides. Now, let's see how this works. Okay? So I want to go up to the top of page 8. And here we have a triangle that's given. Now, the author's got an example here for you in the text, but let's run through and look at it. Now, the first thing I do is I notice I've got this triangle and this triangle. Always first look, are the angles the same? We've got a 90-degree corner, 90-degree corner. Conversely, I've got an angle, 36.52 degrees. Here's that same angle. This one's 53.48, that one's 53.48. Angles are all equal, it's a similar triangle. Now, we don't know the length of all these sides. We know this is 20, this is 15. These are the two legs. The hypotenuse is alongside, right? On this one, we know the hypotenuse. We do not know this leg, but we know this one. How can I solve for the missing sides on both of these triangles so I know the lengths of them?
The Pythagorean theorem?
No. Well, we could, but we're not going to use that. We're going to use similar triangles. This is a different way. We get to the Pythagorean theorem in Principle 8, which also works here, Declan. Okay, but we're going to stick with the concept of similar triangles or proportionality to solve these. Okay. So I don't mean to shut you down. We're going to get there. Okay, we're going to get there. All right, so let's do it. How do you do this? Always set the like sides together. Because you're going to have two legs. Leg, 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 leg. Hypotenuse, hypotenuse. Just look for which sides match up. This is the shorter side. Visually, you can see that, can't you?
Mm-hmm.
This is the shorter side because you're given that information and it's also visible. So if I was doing a cat, I'd draw them, and then I could measure them, right? Well, be that as it may, let's take the small one of this and set it proportional to 15. Okay, so I'm going to take 11.25 and I'm going to divide it by this side. Or I'm going to do a proportion, right? Now I want to set that equal to any other set. So I can set this equal to, let's say, this side and this side. You have to use the same sides. So I'm going to call this side, we don't know what this is, right? So let's call this side TY, because it goes from point T to point Y. So I'm going to still put this up here, TY, over this one, 20. Now here we've created a proportion equation where I've set the relationship of two like sides equal to any other two. We've got 4 variables in here. We have to know 3 of them to solve for 1. At this point, you have to isolate your one variable. Okay. So how we're going to do that is I've got to move the 20 out of here and leave this one alone. So I'm going to times this by 20 and times this by 20 since it's in the denominator. 20 divided by 20 is what?
1.
1. So there's a 1 there, but we don't need to show 1 because anything times 1 is itself. Over here, I'm going to take 20 times 11 1/4. Okay. So what does that equal? Can
225.
somebody punch that number, please?
225.
And that's right on, because quarter, yeah. Can somebody confirm that number, please?
Yes.
Okay, 225 is right. So here's what I'm left with my equation. Now I'm going to take 225 divided by 15. I'm sorry?
15.
15.
Yeah.
So now I've got that side TY is equal to 15. I now know this. This guy is 15. Can we do the same thing to find the hypotenuse of this one? Yeah, I would take any two sides. I know these two, right? So let's take 15 divided by 20. That is going to be equal to, here's the small one. Always keep the same on the top. So if I put this in the top, I've got to put that in the top. And it doesn't matter which way you put them. They're still going to work out okay. So this would be 18.75 over, let's call this PR. Now this one, we've got a number, or excuse me, a variable that's in the denominator. So let's look at this math and walk through the steps. Whenever you have a variable in an equation, you are trying to isolate it. You are trying to get it on only that variable on one side of the equation, and you need it in the numerator, where the numerator is in the top. Okay? Because I got numerator and denominator, right? Does everybody understand that, those two terms? Okay. So what I've got to do is I've got to get this alone on one side of the equation, plus I need it in the top portion of the equation. So we're going to have a couple more steps. I'm going to take all of them. The first thing I've got to do is take this and get it into the top. And the quickest way to do it is to put it over here. So I'm going to times both sides by PR. Whatever you do to one side, you do to the other side. So there's PR and PR. So I'm timesing both sides by PR. This PR divided by PR is 1. So I'll say that it cancels. And I'm left with, let me kind of move this over here. I'm left with PR times 15 divided by 20 is equal to 18.75. Now I've accomplished in getting PR into the numerator. Now I want to get these two terms over here. Remember how we do that? Invert and multiply? Okay. So in essence, I'm going to take this side and times it by 20 over 15. And I'm going to take this side and times it by 20 over 15. This 20 cancels with that one. That 15 cancels with that one. That leaves me PR on one side is equal to 18.75 times 20.
375.
Is equal to 375, and that is still divided by 15. We can run that last number now.
It's 25.
PR is equal to 25. Do you see how proportionality works with similar triangles? Pretty slick little process. Okay? It really is. Works quite nicely. There's a couple other examples in this text on proportionality in these pages. If you don't feel clear on that, you should look through those, or come see me and we'll make up some similar triangles and we'll run some figures and make sure you do understand what you're doing. You will be using this going forward. Okay? I found similar triangles to be very useful in industry. Principle 8 on page 9. This is basically analyzing an isosceles and an equilateral triangle and how these work for you. So an isosceles triangle. Does anybody know the definition of that? Isosceles. Two sides are equal, two angles are equal. Okay, that's an isosceles. Equilateral triangle, this is one of our regular polygons. What's the definition of an equilateral?
All three sides are the same.
All sides are equal, all angles are equal. Now, in essence, what we're doing here is doing bisectors. So the top one's your isosceles. So in essence, what they're saying here is that this angle and this angle are equal to each other. This side is equal to each other. So if you take this one angle that's not the same and you draw an altitude or you bisect it, you create two
Right.
congruent right triangles, or two triangles that are equal. Okay, does that make sense? Isosceles, everything's equal. Sides equal, sides equal, sides equal. Here I can take off of any side, go perpendicular, creates two congruent triangles. And it doesn't matter which side. I get the same thing if I go this way. On an equilateral, it doesn't matter. Isosceles, you have to come off that one angle that is not equal. So just a couple ways to create some like triangles. Principle 9 is the Pythagorean theorem. I want to skip that for a moment. Okay, we're going to come back to that. I'm just making, Declan, I'm just making you wait so that the result will be that much more beautiful. Principle 10, we covered back in drafting 131. It is a formula to help you solve for interior angles. Okay. The formula is given right here. Now this is any polygon. It's a formula for solving for the sum of the interior angles. It does not matter if the polygon is a regular polygon or a non-regular polygon. Remember, a regular polygon is like an equilateral triangle, a square, a hexagon, an octagon, pentagon, all these shapes where the sides are all equal, angles are all equal. Or, okay, such as these, or something that's a trapezoid type of shape, or just an arbitrary shape. This formula will solve for the sum of all the interior angles. The only time this falls down, this formula, is if you have a circular side to your polygon. Okay, and you can't have those. So you gotta have linears. In essence, how do you use it? The sum of the interior angles of a polygon is equal to n sides, that's the number of sides, okay, minus 2, and you times that by 180 degrees. So since we're dealing with triangles in this class, how many, and triangles have all linear sides. What is the sum of any triangle's interior angles? Now, how do you get that? Plug it into the formula. I've got n minus 2 times 180, right? Well, n in this case is 3. All triangles have 3 sides. So 3 minus 2 leaves me 1. 1 times 180 leaves me 180. So if I know any two angles of any triangle, do I always know the third? Yeah, I'm going to take 180 and subtract the other 2. I don't have to use trig, I don't have to use Pythagorean theorem, I don't need anything. It's plus minus stuff. If you have something like this one, which has 4 sides, what's going to be the sum of all these interior angles?
360.
It's going to be 360. 4 minus 2 is 2, times 180 is 360. Can we solve for this angle right here? Yeah, we got the other 3. What about this guy? 1, 2, 3, 4, 5, 6. Did I count that one twice? Let me start at 8. 1, 2, 3, 4, 5, 6. Okay. So 6 minus 2 would be 4 times 180 should be 720. They run you through an example on what this is useful for on this guy. So we had to know a little bit of information. They give this, and this. Keep in mind, they're using a lot of the same stuff here that we went over last week. Full circle has 360 degrees, so we can solve for angle 2 based off of that one. They do that right over here where they come up with 246. Yeah, I think that's kind of it, right? They went and did angle 1 because we know all the other angles now. So we took 720 on this guy minus that angle, that angle, that angle, that angle, and that angle. Whatever's left has to be the last one. So again, another useful little calculation. I know that's a review for us, but probably one worthwhile going over. Let's go back to Principle 9. The Pythagorean theorem. In essence, what this states, and this is a geometric rule. You could even call it a geometric law, where a mathematical law is something that is provable time and time again, right? So in this case, this is a mathematical law. It's geometric in nature, though. Okay, what it's basically saying is if I know I got one side and I got another side, okay, the square of this side and the square of this side has to equal the square of that side. Has to. Doesn't matter. And it turned out to be true. They don't run you through the proof of this, but they do give you this relationship. Now, there is something that you need to know. Here is the Pythagorean theorem right here. C squared is equal to A squared plus B squared. Is this new to anybody in the room? Can I see a show of hands? We've all seen this before. The thing you got to remember on this is A and B are equal to the legs. And it doesn't matter how you label them. There's two legs. C is always the hypotenuse or the longer side. Remember that. Now, if I go to solve for this, they got A and B listed here. They're the legs of the triangle. The hypotenuse is listed as C. Whenever you do this, the C must always be on the hypotenuse. Does it matter, though, if I call this side B and that side A? Absolutely not. Doesn't matter one bit. So your legs are interchangeable. The hypotenuse is not. One of our most famous triangles that we deal with controls this, where I have a 3, 4, 5 triangle. Now, there's one other caveat I never mentioned. See this angle right here in this corner, that little square? That means it's 90 degrees. You can only use the Pythagorean theorem on right triangles or triangles with 90 degrees. That's the only time this is true. That C squared is equal to A squared plus B squared. If you have a triangle that does not have a 90-degree corner, you cannot be using this. It is not valid. Okay? So if I have an equilateral, how do you solve those sides? I drop an altitude down and create two congruent triangles that are right, because an equilateral is not a right triangle. I solve for one and then use it to get the other one. All right, so we know those are congruent. Why is this a famous triangle? Andy, I'm going to put you on the spot. You're a construction guy.
It's the framer's rule.
It
They
is.
don't know it's called Pythagorean theorem. They're not smart enough for that. But they know that if they measure one way 4 feet and 3 feet the other way, that if their 2 points don't match, they're not square.
That's correct.
At 5 feet.
This
So
is the
everybody
way
calls it the
square-
3, 4, 5. Or 6, 8, 10.
This is the way, yeah, framers square corners. If they're putting a wall together that comes at 90 degrees, what do? They find the corner, they measure 3 feet in one direction, 4 feet in the other direction, and then pull their tape to the hypotenuse, and it better equal 5, or they didn't come off that point square. It can be 3 inches, 4 inches, 5 inches, or it can be 3 feet, 4 feet, 5 feet. Or it can be 3 miles, 4 miles, 5 miles. Units don't matter. Any equivalent of this also works. 6, 8, 10 also is always a right triangle.
After you get past that, it's too much math.
Stick with the 3, 4, 5. It works. When we go do action on Tuesday, we're going to use this to get a square coming off a wall. So it's just a nice triangle to know. This is always a right triangle. Now, let's use the Pythagorean theorem to prove that it's right. If I know this side is 3, this side is 4, this side had better be 5 or it's not a right triangle, correct? Let's run it through the equation. So in this case, I'm not going to say what the hypotenuse is. That is C. I will say the 4 is an A and 3 is a B. So I label my triangle real quickly with my letters. So C is equal to A squared plus B squared. Let's plug in our numbers. C squared is equal to A is 4. 4 squared plus 3 squared. Just so you know, do you know where your squared button is on your calculator? Just want to make sure you know where that's at. It should have a little, like a caret with a 2 next to it. By a caret, a little symbol, something that says like that. That's what a lot of them are. Or it might have X with a 2, like that. Y'all see it? Okay. So if you plug this in, you should know that C squared is equal to 16 plus 9. Correct? Let's do the math. C squared is equal to 25. Now, how do you get rid of a square on this side?
Root it.
Take the square root. So we're going to take the square root of both sides. That square cancels with my square root on this side.